we can represent any signal, such as images, in the frequency domain. Then we can consider segments in this frequency domain, the so-called subbands, and examine the behavior of the signal in each of these subbands. The characteristics of an image differ in each subband. Some are low frequency subbands, some are high frequency in one dimension and low in the other, and so on. Then the main idea in subband coding is that we can now adapt the compression scheme to each subband. This means that different parameters can be utilized for the same encoder, or that a completely different decoder can be used in each subband. Therefore, there are a large number of possibilities. One of the issues, of course, is to design appropriate filters that will allow us to perform this subband decomposition, filters that will allow perfect reconstruction of the signal. We discuss and analyze all these concepts in this segment. So let's have a specific look. The idea of subband coding is quite interesting and intriguing. So we first use a bank of filters to divide the image into subbands, and each subband contains a set of spatial frequencies. So each subband has reduced bandwidth with respect to the original image. If the subbands are of equal size, then we're talking about equal rate subband decomposition. If, on the other hand, they have different bandwidths, then we're referring to as multi-rate decomposition. The main idea from this decomposition is now we can exploit the properties of each band and use a different compression scheme to compress the various bands. So different bit rates or different coding techniques can be used for each subband by taking advantage of the properties of each subband, and also by allowing for errors to be distributed across subbands in a visually optimal manner. So this is a celebrated approach that has found applications both in still image compression as well in video compression, as well as in speech and audio compression. Some of the most successful audio compression standards are based on subband decomposition. So the principle of subband decomposition is demonstrated here. We show it for a one-dimensional signal, but also show a 2D signal in a few slides later. So we have the analysis filter bank and the synthesis filter bank. So we see that the original signal is input here. Then we use a bandpass filter 0 to bandpass filter m-1. After filtering, the signal is decimated, downsampled by a factor of capital M. We assume again we have M such subbands. And after this decimation, we encode this subband separately, using a different encoder per subband. The compressed signal, it's either transmitted or stored, the two important applications in image and video compression. At the other end, the decoder, we have the synthesis bank of filters, so each subband is decoded separately, then it's upsampled by a factor of M, and then it's bandpass filtered and all the subbands are added to give an estimate of the original signal. These are operations that should make perfect sense to you at this point because we covered them earlier in class. We saw what happens if we downsample is the spectra overlap. We have the problem of aliasing. That's why we first low-pass filter or bandpass filter before we downsample to avoid aliasing. On the other hand, when we upsample, we introduce M0s in between the samples, and then we use a bandpass filter to extract one replica of the spectrum, because what happens in the frequency domain, I have replicas of the spectrum through this introduction of zeros, and through this bandpass filtering, I pull out one replica and I pull the signal in the original resolution. Here is the block diagram of a two-channel subband decomposition. And having this actually a two-channel, I can then cascade it and end up with multi-band as well as multidimensional signal subband decomposition. So we see the H1, H0 filters here. The H0 is a low-pass filter, H1 is a high-pass filter. So decimation by a factor of 2, encoding, upsampling by a factor of 2, and here are the upsampling filters F1, F0. Conceptually, the upsampling filters are undoing what the downsampling filter did, you might say, and there is a lot of work on how to design these filters, H0, H1, F0, F1, so that in the absence of compression, I have perfect reconstruction. We don't have perfect filters. If you implement the spatial domain, they have a pass band, a transition band, and a stop band. And there are, for example, the quadrature mirror filters that give you perfect reconstruction. It's a topic that has seen a lot of activity in signal processing, and there are quite a lot of results that one can utilize. So this is what is done in practice when, with two band decomposition system, I want to build a multiple subband decomposition system. So I start again, I show it as one-dimensional signal. You break it into a low frequency band and a high frequency band. So x of omega, if it's shifted by pi, it gives me, if the first one is a low pass filter, it results in a high pass filter. So downsampling takes place here. And now we will take the low band or the low frequency band and split it also in its low frequency and high frequency component. I can take this low frequency band and further split it into two. I can take this high frequency and further split it into two. So in this particular example, I end up with 2, 4, 6, 8 different subbands, and they have the name of this quad tree in essence. So this is the LLL band. Only low pass filters were applied to this one to obtain this band, while this one, the first filter is low pass, the second is low pass, but the third one is high pass. So pretty much you have all 8 combinations of these different letters, and the last one is HHH. So the filter was filtered 3 times by high pass filter to give us this band, and this band is here, the highest frequency band. The first one is down here, the lowest frequency, and so on and so forth. So again, having one good pair of decomposition, I can cascade it this way, and I end up in an equal rate as shown here, obtain as many bands as I want in this multi-band decomposition system. And since this pair has also its reconstruction, perfect reconstruction pair, I can also go from this 8-band decomposition here, for example, to perfect reconstruction using the pairs that I started with. Here's the picture of subband decomposition in 2 dimensions. If I have a filter that can break the frequency spectrum of a signal into 4 bands, so it's a 4-band split decomposition here, then I can use that in a cascade to obtain as many bands as needed. So in this particular example here, you have a 4-band split, and this is the 4-band split. This is the LL band, and then LH is here, right? Because it's centered at 0, you can do the periodic extension and see how these bands look like. And then we have the HL band and the HH band. So in the first pass, I split the image into 4 bands, and then, for example, I can take the low frequency band and split it into 4 additional bands. So that's how the picture is going to look in the frequency domain. Here are the 4 original bands, and then the low frequency band was split into 4 additional ones. So this is actually an example of a multi-rate subband decomposition, because the bands are not all of the same size or of the same rate. And in practice, that's how we obtain subbands, either equal rate or multi-rate, just using one pair, either 2 filters for a one-dimensional signal or 4 filters as shown here for a 2-dimensional signal. Here's one example of the use of subband decomposition. All these examples again were generated using VCDemo. The original image is shown here again, and this is a 4-band decomposition using 16 tap filters. So the number of taps is the number of samples in the impulse response of the filter. So you see here the 4 subbands. The low-low subband is just a decimated version of the original image. It was just low-pass filter. These are the low H and HL bands, so they show the high frequencies in the horizontal and the vertical direction. And this is the HH band, which shows the high frequencies in both directions. By and large, you see some structure, of course, in the low frequency band, and then in the LH and HL bands, and the HH band by and large looks like white noise, doesn't have much structure in it. So for these 4 bands, for the first one, the LL, DPCM was used to encode the coefficients. And we talked about DPCM, it's clear what we are doing here. It's differential pulse code modulation, so a prediction model was built to predict and then correct the intensity values of the low-low band. Now for the other bands, the combination of high and low frequency and high-high band, PCM was used. So no transformation was done, but just reduced the number of bits in representing the samples. And the rate was 1.6 bits per pixel. So here is the resulting encoded image. The PSNR is 36.5 dB, so it's definitely of high quality. As I mentioned, anything above 30 dB represents a very close representation of the reconstructed image, very close to the original one. Here's a second example of the application of multi-rate now subband decomposition, the original image. So it's split first into 4 subbands, and then for the low subband we further subdivide it into 4 subbands. So it's certainly multi-rate. It's a 7-band decomposition, and also 16 tap filters were used for this decomposition. Then here are the quantized subbands. The first subband, the low-low, DPCM was used for that, and for the rest, PCM at 155 bits per pixel. And we see here the encoded one is of similar quality, slightly higher quality than the previous one for a very similar bit rate, but certainly there is more computation that is involved when you go to more than 4 subbands. Here we have, again, 7 subband decomposition. So we have reached the end of week 9. 3 more weeks to go. 75% of the course is over. Congratulations to all of you. You should really feel proud about your accomplishment. During this week, the second week out of 3 dedicated to compression, we talked about lossy image compression. This is a very important topic since we are surrounded by a plethora of applications depending on image compression. We discussed and analyzed the fundamental topics and covered some of the intellectually interesting and practically useful techniques. We talked about the important concept of quantization, both scalar and vector, and covered DPCM, fractal encoding, transform encoding, and JPEG, and finally we briefly covered Subband encoding. Prediction and transformation of the data are 2 very fundamental and important topics encountered everywhere in signal processing. We presented encoder in terms of 3 important building blocks and tried to point out the differences and similarities of all techniques we described. There was nothing terribly mathematical in the material of this week, except maybe for the material on fractal encoding and the derivation of the optimal quantizer. So I hope everybody feels comfortable with this material. The material, I believe, allows you to understand the image compression technology around you, use it, and also be able to potentially take the next step in pushing the envelope and developing the next image compression technique. Next week, we'll talk about the sister problem of image compression, that of video compression. So, see you all next week.